Okay, so good morning, everybody. My name is Kazuya Takeda, as Iijima Sensei introduced. I am, because program coordinator of this graduate program. Actually, this is a main part of graduate program, which is called Real World Data Circulation Leaders Program. And I am the program coordinator. So I am going to start this lecture as the first lecturer. And because this is the first lecture, so I'm very happy to share with you about the idea of the real world data circulation. By the way, how many students took my lecture for the Graduate School of Informatics last year? Did you? So I'm sorry, almost all parts are duplicated in that lecture, but anyway, because this is both my own research and also RWDC program's goal. Iijima Sensei slightly mentioned about the keywords of RWDC. Those are data acquisition and analysis, and also implementation. So why data circulation, I think, is important is that because a lot of real-world complex problems cannot be solved by simple equations or algorithms. We need to adapt to the ever-changing social behavior of human, or huge amount of data signals associated with our everyday life. In order to cope with such a complex situation or deeper knowledge of human, we need definitely adapt to the new situation or how do I say, change the system itself drastically day by day. So the RWDC idea is one of that, which essentially capture real world data, real world through data like IoT. You have smartphones. I will talk about vehicle, but vehicle has a lot of sensing systems. And also, we have a camera there, or microphones, or accelerometers, as those things are quite common to capture the real world. Of course, those things cannot completely understand the situation that we are facing but we definitely can get some ideas about human behavior or social behavior. Actually, in the previous time slot, just like 1 hour ago, I was talking about joint probability. Okay, because I thought I am teaching the information theory to the graduate school student of information science and also electrical engineering. And the key idea is to know the joint probability, which is the association of two different things, like the temperature of the day and also the market sales of ice cream, for instance, in a Famima convenience stores. So those two different things can be differently captured through data, but once you get a data and you get association with two different things, then you can easily, or not easily, but probably very difficult maybe, but you can get somehow causality of two different things. How temperature affect the social behavior of us, things like that. Those can be only done by the data circulation. Just simply through capturing the data and associate those data with the analysis phase, it is not enough. Because that is, that gives you some sort of knowledge, but you cannot verify it. So in order to verify that idea, you need to re-implement those ideas into the real situation. Like, for instance, when the temperature is very high, then you are going to be high, then you can increase, sales stocks for the ice cream, for instance, and you can see what happened. There will, if your hypothesis is correct, then you get some, good sales. But if your hypothesis is not good, then it can be, different. For instance, when the temperature is high, but it is not a direct cause of the sales, but you can imagine some event at that moment around the university or near the Famimar there, and that was the direct cause of the changing of the sales values. Then that's a completely different thing. So we need to we need to continue this again and again, and then we can accumulate a lot of different knowledges, like GAFA people do. So we like to have you had a kind of this in your mind, because you are skilled engineers or you are skilled researchers. You're gonna sooner or later facing a very difficult real-world situation, real-world problems, and there's a lot of ways to solve it, because of course you can apply your basic knowledge on a theoretic aspect of the phenomenon, like astronomy or mathematics or physics. Of course, those are very quite powerful tools. But nowadays, what we are facing at is much, much more complicated. So the only way that we can improve on the top of the giants is to utilize the real-world data and circulate them. That finally or eventually gives you a big value, like big sales or deeper understanding of the systems or influential power to the real world, things like that. So that is a fundamental image or understanding of the real-world data circulation program. So we have students from economy and engineering and medical and informatics. Those people are jointly working together toward to master or to understand this complete idea. So in this short-term lecture, I'd like to project this idea onto my own research field, which is the human behavior understanding or human behavior signal processing, which we call. We particularly study on driving behavior of human. That is because it has a lot of applications, and also very interesting because vehicle has a lot of sensing systems currently. Therefore, we can capture a lot of data through driving. And also, there are a lot of very beautiful theories about control theory, controlling vehicle dynamics, physical systems, and those are fantastic. And also, we have a big industry related to vehicle. So when our idea is implemented on a current social system, we can get big money simply. So applying our knowledge or theory to the vehicle application is quite fantastic to me, right? So in that case, what we are doing now in terms of the real-world data circulation is very simple. We get data associated with driving. Those are vehicular behavior and also driver behavior and also surrounding vehicle behavior, things like that. Those are captured through physiological sensors and also physical sensors and also image like by camera and also sound or those things. So it's pretty easy to get data from vehicle, and it is also easy to scale. We have a huge number of cars running on road, so this is easily extendable. And analysis part, this is very, very interesting for me to study because we are very familiar with mechanical systems, but not much at driver behavior or human systems. we do not have firm theory about human behavior. Of course, it is not, because we are not a machine. We are not programmed, computer. But exploring those human behavior is quite, challenging and interesting to me. And then implementation is simply building a vehicle. Actually, our colleagues in a leading program has, in total, maybe 5 or 6 startup companies, all associated with the autonomous driving systems. Some student has a company building a map for the autonomous driving. Some student is developing a sensing algorithm for the autonomous driving. Those students all come from a leading program. So I'm very happy working together with them and implement our idea on our open source platform of the autonomous driving, which is known as AutoWare. Now currently it is worldwide famous. And we have a lot of colleagues worldwide who use that software. And so I think, to me, this is very fantastic application and interesting challenges. And to my deep regret, since I'm working as a program coordinator, and also, actually, I'm working as a, presidential supervisor or presidential advisor to our university president, and a lot of things have to be done under my, signature or things like that. So I do not have time to deeply or to devote myself into the research currently. So I cannot talk to you about my own research results or my own research ongoing project. I'm very sorry about that, but I and my students are working on this, and I will slightly mention about recent research of them, if I have time. So I said that human behavior is very difficult. When I project this fact onto the intelligence that you need to drive a vehicle, or in other words, the program for the autonomous driving system need. So I roughly subdivide those knowledge that the autonomous driving system has to have into 3 different categories. One is physical knowledge. This is very important. Without this knowledge, you're going to easily hit the vehicles nearby or collide the new vehicles. And physical knowledge is quite simple. For instance, you have a motion equation. How fast you can go with regard to the distance to the foregoing vehicle, which is running under the certain speed. By giving such 3 variables, then you can calculate if the vehicle will hit that vehicle or not. Okay, so such physical knowledge is fully implemented in our recent vehicles, like to avoid the collision, and it is quite effective actually. So the physical knowledge can be implemented through very simple lines of programs, lines of codes with certain parameters. Of course, you need to tune those parameters, and also you need to, improve the performance of the surrounding, environment recognition. But still, the system is being under the control of a very simple system. On the other hand, if you try to run vehicle autonomously, then you definitely have to teach the traffic rule, local traffic rule to those vehicles. That is actually not pretty much easy, right? Because rule sometimes mean rural regulation or regulation defined by law. That is written in natural language. Therefore, we have to make machines, mechanical system understand the natural language. But furthermore, because rule doesn't, have only such a governmental regulation, but in some cases, we have a social rule. For instance, it's not easy. Are you guys drive? If you drive, then you may familiar with some funny, how do I say, ways. For instance, I used to commute by my car, go through Heiwa Koen, and there's a wide road just in the middle of the Heiwa Koen. And in the morning time, because traffic is rather busy, they used that one lane splitting into two. You know what I mean? So actually, there's no line in between, but people know that the righter part of the lane should be dedicated for the vehicles which will make right turn in the T intersection, and the left part is used for the left turn. There's no rules, there's no description, but for the customary, people use the road for such a way. But once who are very new to that system comes, he tried to go in the middle of the lane, which is very annoying because people like to use the road more efficiently. Anyway, so such a how do I say, traffic custom or traffic how do I say, ways of using the road is not written anywhere, and you cannot know without experiences. So such a social rule should be also known by the vehicle, and that is not easy to teach again. But what I'm mostly interested in is this one, empirical knowledge, or in other words, personal knowledge, which sometimes is equal means with the preference. How fast do you like to go? How rapidly do you like to change the lane? Or if you like to go past this foregoing vehicle or not. Those things are completely different from driver to driver. And this is, directly associated with the comfortable driving of each individual. So imagine that this is physics. Therefore, if you read the textbook with the physical systems, then you can somehow get this idea. This may, maybe, programmed or coded if you are carefully observe the local traffic systems, maybe. But some part of them is not easy. But this one cannot be implemented without, examining or without asking each individual people about their preference. And in general, that is very difficult. Suppose that you are the manager of the vehicle industry, and you like to design a special vehicle which is good for a particular person. And that car will be sold to millions of people. Then what can you do that? There are only two ways. One is to customize you. One is to ship, product the customized vehicle by yourself. And the second way is to make the user customizable, to make the user customize their own car, which means that you produce the vehicle which is customizable by the user. So this is not an easy task, but I think future vehicle or future car has to have this functionality, definitely, in order to improve the value of the vehicle or value of mobility. So one way to do that is data circulation. That is my point. So I'm going to skip several slides because I don't have time. But anyway, what I wanted to tell you by these slides is that actually I like to highlight two videos. I like to highlight two videos. One is produced by BMW, and one is Google. They also introducing their technology of the autonomous driving, but BMW people try to show that this autonomous car can precisely and accurately controlled in order to run very fast. But Google people showed the video that moving becomes very fun to everyone. It's a completely different idea, although they are heading at the same direction. So the value of the autonomy are quite wide and diverse idea. And in order to make, the best value for each individual customer is quite important for the market on the industry, and also the technology for that is quite important. So for instance, as I mentioned that we have a mechanical system. When we have mechanical system, then we have a very solid theory about controlling. For instance, there is a spring model, which is equivalent to the second order differential equation given by this. And this is, if you think about the analogy of a spring, it is easy to understand. This is the natural length of the spring, and this is the actual length of spring, and this is the Fock coefficient, and m is mass, and x dot dot is of course acceleration. And this describes that once the length of the spring becomes different from the natural length, then the force which is counter direction to the length of the spring make the object have acceleration. So for instance, when the car following, suppose that this is a spring, then this driver tried to keep the natural length or natural distance to the foregoing vehicle. And once the vehicle becomes closer, then he decelerates. And once it is getting further, then he accelerates. And the natural trajectory of this movement becomes like this, because this is one of the typical solution of this differential equation, which is known as the sine and cosine of the time function. So this is very, very fundamental physics. And how can we describe human driving behavior by that mechanical system analogy? That is one big issue. And we don't see any big circular trajectory like I showed in the previous slide. Obviously, this is a following distance, and this is a velocity. Therefore, if your distance get further, then the velocity becomes more. Therefore, this trend is very natural, but there's no big circle. Okay? Probably there's circles here, here, here. When you see local behavior of this solution or trajectory, then it becomes a circular movement. Therefore, we can see somehow, spring is imposed in each individual state. Right? So we have several steady states here, there, which has more data. And under that state, people try to keep the distance, and that movement becomes pretty much similar to the spring model. So this is very interesting to me. When you see the line itself, we cannot find such a circular movement. But when you look at, or when you impose the data distribution, how does the data distribute in the real world, then you can somehow get a hint to find the local circular movement of the driving behavior. So I think combining physical knowledge with the data knowledge, which is given simply by counting how frequently such combinations of following distance and velocity observed. When the height of the mountain is high, then simply the count is more. Okay? So data science is nice because we can somehow we can get somehow the very informative hint to understand the situation, even it is very complex. And so instead of using the differential equation, we can simply find a PDF, probability density function, by observing the real world data, and that can directly be used for the source of the knowledge, like physical system, this. So this is not a, directly describes the real world data circulation, but this is a very tiny part of the real world data circulation. But real world data can be somehow modeled and can be used for understanding the complex systems. That is obvious to me from these experiences. Actually, we have applied this technology to identify who is driving, and that was quite successful. And also, we applied this to the lane change prediction, so, which I will mention later a bit again. So data collection is quite important, of course. And we needed a lot of sensing devices in order to start our research, and we have collected more than 800 drivers driving behaviors in a real driving. But that was, 5 years, 10 years ago. Now you have a big infrastructure to collect the data. Actually, vehicle has a lot of sensors, and those sensing signals can be tapped through LAN interface of a vehicle, which is known as CAN, C-A-N. Of course, that is not, disclosed to public, but you go to a motor car company and you get some sort of agreement, then you can get information about CAN signal. And that gives you a lot of sensor signals. And also, video camera is quite cheap. And nowadays, you can get a LiDAR 3D point sensor signal. That is also very informative about the nearby vehicle location and also the building locations. So if once you get a vehicle data, then you can understand the real-world behavior of this driver through these sequence of data. This is the picturization of data that we have, we get from the data, real-world data. And you can see, for instance, this is the scene that he or she will making. She will be making a lane change, and eventually she gonna operate the steering wheel, and then because she has somehow stressed with adjusting her way to go, she got a little bit nervous, and the vital reaction could be or can be observed from the signal, and these are bumps to go over the lines. So these things somehow gives you the idea of what is happening here, and video is very informative again. But for the computer systems, all these things are a bunch of numbers. So we need to write a code to convert these bunch of numbers into what is going on. And thanks to the deep learning technologies, the accuracy of such a conversion becomes more and more accurate. But of course, you may need huge amount of data and also ground truth. So here's the ground truth. This is the highway, no task, and there's a 2-lane ways and something like that. These tags has been given by manually given by these tags, and this is not an easy task. We used more than millions of dollars for giving these tags to our 800 driving behavior corpus. It is very expensive and it is very tedious. But without these ground truths, we cannot build any kind of deep learning system at that moment. But I don't know. Currently, we have a lot of technologies which enables self-learning. So I don't know. I hope some of you may improve this recognition system and be successful in making money. But currently we need definitely ground truths for training. So the biggest issue so far is to find a conversion system which gives you this is analysis and prediction and making the function which maximize the value of driving. So again, probably time is not so much. So to me, or to our research group, one of the biggest fun of driving, or one of the biggest value of autonomous driving system is to reproduce their own driving that the owner of the car prefers. Whatever it is very, very, very safe or very, very, very conservative, if the drivers or owner or passenger of the autonomous driving vehicle feels it is too slow or very boring, it doesn't, it cannot be said that that is a very good autonomous driving system. So, of course, safety is the first issue, but also we need to reproduce their own driver's preference. So one way, one aspect of that preference is, for instance, the intervehicular distance and how to keep that distance. We can, probably keep the preferred distance to the foregoing vehicle in, various manners. You can quickly change the speed in order to keep that distance, or you can gradually, change the speed in order to keep distance. Those way of driving are quite flexible. So once we get a data distribution, which is the connection between the distance and the speed, then following this distribution, we can somehow get an optimal value, which is most frequently observed value combinations, and that is one strategy to reproduce the personalized distance keeping way. For instance, these two profiles are observed under the same driving condition done by simulator research, and driver A and driver B completely had a different profile because their preference. Driver A likes to keep the driver B tried to keep the distance very constant, and driver A did not care that intervehicular distance. And for the driver B case, in order to keep the distance, he operated a lot of axle and brake, but the driver A didn't. So these differences are quite interesting evidence that driving behavior has a preference. And by using the scenario, by using the probability approach, that we have studied, we can regenerate the very similar driving behavior to each individual drivers. For the driver B, blue and red lines are predicted and original lines, and driver B are same. So we can somehow produce quite a similar intervehicular distance based on the probability theory like this. And only what we have used was only probability density function. So as lane change trajectory. So lane change trajectory is another important way of driving, and that also very differ among drivers. And this trajectory can be also parameterized through a three-state Hidden-Markov model. And by using this three-state Hidden-Markov model, we can generate highly probable trajectories and choose one of them may fit to the preferred or comfortable lane change trajectory for the particular driver. And another aspect of the personality of driving is the risk feeling. So this is completely subjective to the people, right? So for instance, this is a very dangerous lane change, but it still depends why and how much you feel danger at the same situation. So we had 10 evaluators of the video, and each individual evaluator saw these 1,000 videos of the lane changing and evaluate the risk by their own feeling. And of course, that feelings differs among evaluators, and which means that when you design an autonomous driving or driving assistance system, you have to obey such subjective driving risk feeling for each individual driver. Of course, you have to design the system that you do not collide with the surrounding vehicles. But furthermore, you may somehow adjust to the subjective risk feeling of the driver. And based on the data, we can somehow model the risk feeling of the particular evaluators. That was what we have studied through the data. For our case, we used random forest technology, which is based on the decision tree learning, and that is a part, kind of machine learning, but somehow very descriptive machine learning, not like a deep learning. But by applying random forest method, we can choose, or we can know which variable is more influential to the personal risk feeling. For instance, some subject feels or thinks that velocity is quite important, and some were sensitive, and some subject is very sensitive to the distance to the left lane and in front of the vehicle particularly, or something like that. So those are difference of the sensitivity to each individual traffic variables can be somehow modeled by this random forest technology. And good thing of this method is we can understand which is the more significant to each individual driver. And based on that knowledge, we can change the way of the controlling the vehicle. Even you can go the same way. You can design a different acceleration, deceleration profile for each individual driver. Okay, so such project is now undergoing, And she is also a student of the real-world data circulation program. And she is now staying in Ohio State University, where the people are developing a very nice model predictive vehicle control simulation system. And that's very nice for her to jointly working those people and developing this idea and implementing them into real real autonomous driving systems. So this is another aspect, subjective feeling. And I don't go in detail about research. And I think I should conclude this short lecture. Again, this is the whole picture of the real-world data circulation in our driving behavior research. And we have a lot of sensing devices in a car, and we can capture a lot of signals through that system. And we have a nice, solid physical knowledge, but on top of that, we can use statistical modeling method or statistical learning system to supplement this simple system in order to cope with the real world, very complex system. But on top of that, again, we have to implement that system on a sort of a real system and get a response from these real users. And those responses will be also captured through a data acquisition process, and that can be further used for improving the data circulation more and more, which finally gives you a very big value, which could not be achieved by a simple system or a single shot of the test try and error, and because of the big data analysis. So I hope you share my idea on a real-world data circulation, and I hope also like that idea. And if you are interested in this research, you can come to us, and we can discuss more in detail. And this is the end of my talk. Thank you very much.